Okay, now interesting thing about genetic algorithms is you sort of get what you ask for. If you don't write a good fitness function, you're going to get the answer to what you defined in your fitness function. So my first version was basically, don't fall off the table. Is that better when I highlight it?
No.
I will unhighlight it. So the first version was just don't fall off the table. And so what did it learn to do? It learned to not move. Or it learned to just spin, and so it never would get to an edge. That's not very exciting. It did it after a few trials. It would just sit there, and it would move off the table, and then it would go slower and slower until it decided, I'm not going to move. It's not very fun. So then I did a second version, and I changed the fit again. Sorry for the highlight. I gave it extra points if you move forward. So it was an attempt to, I want to force you to move forward so you eventually do fall off, because the whole fun part of this is to do something bad and then learn not to do it. And it learned to get to an edge as quickly as possible and then stop. So it did move forward, and because its fitness function was left motor speed plus right motor speed, it would eventually just go to 255, 255, rush to the edge. That was in state 1-1, which is the two sensors both on the table, and it would get to a state differently, either 0-1, 1-0, or 0-0, and in that state, it would stop. Perfectly valid behavior. It learned exactly what I told it to do.
So you're giving it points for driving.
In version 2, I gave it points for the highest forward velocity, for higher forward velocity.
So when it detects the drop, is that like a pain threshold or something that made it stop?
If it falls off the table, the penalty was negative infinity. It died. So let me scroll down a bit.
How does the robot know that?
I'll get to that in just a minute. The last version, version 3, is if you end up on an edge, I'm going to count that as death, as if you fell off. So I want to discourage it from rushing to the end, getting there, and then stopping. So now we're forcing it to do something more interesting. It has to move forward, but once it's off the edge, one of its sensors, that's death. So it has to quickly learn, oh, that's like fire, that's lava. I can't be there, I got to back up. And that's where we finally got some interesting behavior. So the lesson learned there for me was define your fitness function, what you really want it to learn to do, because it will learn exactly what you ask it to. Kind of like the answer 42. You got to be sure you ask the right questions, right? So let's scroll down really quick. This is just sensors. Motors, really simple, set the speed left and right. And now this is the genetic algorithm. So basically the gene itself, there's 4 different states, GA-num states of 4, and that is defined by the bits of the 2 sensors. So there's 4 different states. And for each state, there's 3 values in its gene. And that is GA left, GA right, and GA delay. So in other words, when I'm in this state, I'm going to set the left motor to this value, I'm going to set the right motor to that value, and I'm going to do a delay for so many milliseconds. And that's it. That completely defines its behavior. So there's 12 values for that. Again, death is negative 32,000. Using an Arduino int, it's only 16 bits. And then to randomize a gene, I just take the number 12, and I pick a random number between 1 and 12. Yeah, this completely randomizes it and just throw random values in there. We initialize it. The mutation algorithm, again, I wanted to do something really simple just for illustration, so it's really easy for you guys to take this and modify it and play with it. What we do is we take the gene is the one that we're going to make a mutated copy of, and we're going to create a mutated gene. So the first thing we do is we copy it over, and then we just take a random number of point mutations. So I take a random number between 1 and 12, and then I take another random number between 1 and that number. The reason I do that, it's sort of a CS optimization. Instead of just getting a random distribution of equal values, it sort of gives you a Gaussian, so you end up with more 1s, 2s, and 3s than you do 12s. So all it does is just shift the number of mutations, so it's not going to completely randomize the gene all the time. And then all I do is I take each, however many, say I'm going to zap 3 of the genes, and all we do is we say, okay, we're going to completely randomize you. We're not going to play the hill climber, we're just going to do plus or minus 10 thing. We're just going to completely zap that gene. And that's all there is, really simple. It doesn't learn as fast that way. Again, like I said, this is an art, and you can fudge this and come up with optimizations and make a genetic algorithm work faster. But the point here is, to me, as simple as possible. This is like the bare bones genetic algorithm. And then we have a fitness function. So the fitness function is, first, we want to wait till, don't start until you're on the table. We want to get the start time because the fitness function, we're going to be running this a long time, and I decided let's just limit your run to 5 seconds. If you die within 5 seconds, you die. If you survive for 5 seconds, then we're going to score you, and that's going to be your fitness. So let's see. So we read the sensors, we figure out what value we're in, then we do the delay, we set the motors, we delay for however long the gene says, and then what I did was the first version of the MotBot, well, it broke. Setting it on a table and having it learn to stay on the table, that's what happens. Like I said, if you can do it in simulation, do it. When you do it on a real robot, you're going to break your robot. So I came up with a clever idea. I put a third sensor on the bottom in the middle. And I decided if I have a small table with a large black border, when he gets here, we can auto-detect and we can tell it, oh, you fell off the table, that's instant death. So that way it could learn without actually breaking. So it's a contrived way of falling off the table, detecting it without actually falling off the table. And that made things a lot better. So this MotBot has not died yet. A real death. And that's it for the, let's see. And then the initial, this was the change right here. Give points for forward speed. So we start off with the score instead of 0. It's just left speed versus right speed. So the idea is learn how to go as fast as you can forward and not die. And then the iteration, this is pretty much what all GAs have. You just take, you mutate what you have, then you score them. So there's the GA mutate, then you score it with the fitness function, and you just compare which are the top ones, that's the selection. Keep the best one, and iterate. So really simple. If you remember the GA, let me pull that up again. Elements of a GA, where did you go? Oh, that was on the Google Drive. Yeah, so there's a population, in this case it's 1, there's one value of what's the current best. Then there's a mutated test that's going to run on the robot. We evaluate it with the fitness function. We select which of the 2 worked better, and then we mutate, and we keep going. So, what we're going to do now is actually turn this thing on and cross our fingers. yeah, really briefly, so let's see, we've got the randomization, we've got a mutate function, a fitness function, and a selection function. And again, this was designed to be as simple as possible. Those are the components you need. So, every time you turn off the power, of course, he forgets it, he's going to start from scratch. So, hopefully, and in other tests, it took about 5 minutes to learn how to do it, which is pretty good considering you're only doing a single test every 5 seconds. So let's go.
Switch over to her video so people can see. Is it okay?
Oh, yeah. Let's put that up there. Maybe if I could get one volunteer to like sit here just in case and stay low, and I'll stay in the back. Because sometimes it, like you said, it does get a lot of speed and overshoots. And this is what I was talking about when I said that this will sort of solve your problems. This thing will learn to stop on a dime. It will learn to go straight. The whole point is rather than try to write all this code, yeah, that's great, that's the AI solution. But the ML solution, which I think is much better, is learn how to do this. Solve it with data, not extra code. Just a quick aside story, the first version of MotBot that actually won the gold medal at RoboGames, who was it that has the one sensor with the LiDAR? And you said that's enough information to solve the tabletop, exactly. It was the same thing, all it had was a ping sensor. And it didn't know that the motors were completely imbalanced. So it would actually learn how to move. It would find the block. It would scan with the ping sensor. And then it would randomly move. And then it would scan again. And it would notice, where did I move in relation to that fixed block based on the outputs that I set the motors to? And it would learn its own parameters. And it took into account pretty much everything because it was empirical evidence based on this surface and a pulse to the left motor of 250 milliseconds at value whatever. It would learn how to do it. So here we go.